Hello and welcome to Cup of Cosmology, the place for all your questions about the universe. My name is Diana Hooper, Charlie to friends, and I'm a postdoctoral researcher currently based in the University of Helsinki, over in Helsinki, Finland. And I'm a cosmologist, so that means that I study the universe, the contents of the universe, how things evolve, how things interact, cool stuff happening inside the universe. I love being a scientist, I love being a cosmologist, and I love chatting to everybody about all of the cool things I get to work on. So for anyone who's a first-time viewer, welcome. For the regulars, welcome back. It is great to have you all here. For anyone who doesn't yet know, Cup of Cosmology is an interactive stream. The idea here is that you people can ask me anything you want about physics, about space, about cosmology, about academia, about Helsinki, about my cats. It's an ask me anything. You can ask me anything, and I will do my best to try to answer your questions, which means there is a lot of audience participation here, and you can all influence the direction the streams take. That said, today there is a specific topic. Often on these streams, it's just me rambling, and based on your questions, I decide what we're talking about. Today, there is a specific topic which was kind of requested or proposed last week, or I proposed it last week based on some questions I was getting. So today we do have a topic. Before we jump into today's topic, hello to all of the regulars I see coming in here. Brad, Scott, John, David Howden, great to see you all. Welcome back, as always. If you haven't done so yet, if you're new here, or if you're just figuring out what to do on YouTube, on Twitch, there's a bunch of buttons you can press that make stuff happen. You can subscribe, you can leave a comment, you can like the video, you can interact on Twitch or on YouTube, whichever platform you are on. Feel free to say hello. I get all of the comments here together. So jump in, say hello, let me know where you're watching from, let me know, how you all doing. Let's just warm up a bit, wait for a couple more people to trickle in, and then we're going to get started with the topic of the day. I see we also have Paul and Ben joining. Great to see you both as well. So, just going to add a disclaimer at the beginning that there might be some technical gremlins today, because as you can all see from the very clear branding up here, I use the free version of Restream to do the stream so that it goes out to both YouTube and Twitch. I know there are other alternatives. I'm happy with the setup. Restream changed the studio about 6 months ago, and I've been refusing to switch to the new advanced studio because honestly, I don't like my software changing. But as of 3 or 4 days ago, they have forced me to change to the new studio. As you know, they gave us 6 months warning. It's fair. But that means I have a whole new studio. On your side, things probably look the same, hopefully. On my side, things do not look the same. So I have new buttons to press. I have different things happening here, which means I'm probably going to press the wrong button. As long as I don't press the big button up that way that says end stream, we should be good. So just a warning that there might be some technical gremlins. However, one very nice thing about the new studio is that I can upload my own music. So if you all have been joining for a while, you know when you join the stream, there's this waiting screen of Cup of Cosmology starting soon with some music playing. And the music that was playing today is different to what's been playing recently. The music that was playing today is one that is actually designed specifically for Cup of Cosmology. It was part of a collaboration I did with an artist back in the HAPS days, Swish Beats. I commissioned this piece of music specifically for Cup of Cosmology. It is the video of it is the music that is in the trailer for Cup of Cosmology. If you've never seen the trailer, it's the first video on the YouTube channel. Please go watch it. I put a lot of effort into the trailer for Cup of Cosmology. Anyway, now I can play my own music, which means I've been able to upload the actual Cup of Cosmology theme song. There is a Cup of Cosmology theme song, which is now what you hear when the waiting screen was open. If you have no idea what I'm talking about, watch the replay. And when you see the waiting screen with Cup of Cosmology starting soon, you'll hear a piece of music. That is the official Cup of Cosmology theme. So now, thanks to the new studio, I can very easily play that. Comment from Paul, just press all the buttons and we'll see. Yeah. Does the new version let me pin chats? That is an excellent question. It does not let me pin chats. At least I don't see a button to pin chats. I have the usual button to show it on screen, so I can show you a comment on screen, but I don't think I can actually pin it. Not yet, at least. We'll figure this out. Comment from David Howden here. Slightly distracted for the first few minutes, processing a few moths into the collection. That is very cool, David. David Howden studies moths. Very cool things, and I love hearing about the moths that you're working with. That's very cool. Okay, so hello, cats. I have Otto up here with me as well. You probably didn't see it, but he just walked past the keyboard. I've gotten very good at turning off my keyboard as soon as a cat approaches my desk. I have a switch to turn it off because he walks past the keyboard. He walks on the keyboard every single day. So now I've gotten very quick. As soon as a cat appears, keyboard goes off, because else he'll press random buttons that he's not supposed to be pressing. Got distracted by a cat who is demanding attention. Where is my other cat? My other cat is suspiciously quiet somewhere. Okay, so let's get started on today's topic. So there are several things we're going to be talking about today, but mainly what we're going to be talking about is Vera Rubin. Vera Rubin was the person who gave us the first evidence for dark matter. Now, of course, science is not an individual effort. This was the result of many, many people. But Vera Rubin is the person who found the first evidence for dark matter. She was an American astronomer. And in addition to doing pioneering research for astronomy, specifically in the field of galactic movements, galactic dynamics, and dark matter, she also spent her life advocating for women in science. There is a quote from Vera Rubin that I like a lot, which is, "There is no problem in science that can be solved by a man that cannot also be solved by a woman." So today we are going to talk about Vera Rubin and the observatory that has been named after her, the Vera Rubin Observatory, or VRO for short. So here's how this is going to work. I'm going to start by just briefly reviewing the life of Vera Rubin with some cool anecdotes, and for that I'm going to use my handy notes because I will not remember all of the facts otherwise. Then I'm going to put Vera Rubin's work in context. We're going to talk a bit about dark matter, why dark matter is important, which you've all heard me do the spiel before of why dark matter is important. But then we're going to talk about why Vera Rubin's work is important for dark matter. And then we will talk about the Vera Rubin Observatory, or VRO for short. And I will discuss the first images that we got from the Vera Rubin Observatory a couple of weeks ago. Like 6, 7 weeks ago, around that, a few weeks ago, recently, within the last, cosmic epoch. So that's the plan. Vera Rubin and dark matter, Vera Rubin Observatory, new results from Vera Rubin Observatory. We have a plan today. Also, just going to say, before we get into things, the Vera Rubin Observatory has many different names. This is also something I'm going to talk about. There has been some kind of transition with the naming of Vera Rubin Observatory. So if you have ever heard of the LSST, the Large Synoptic Survey Telescope, it is the same thing that we are talking about today. If you have heard of the Rubin Observatory, if you have heard of the Legacy Survey of Space and Time, all of these acronyms and names refer to the Vera Rubin Observatory. There's many names for the thing, but it is now the Vera Rubin Observatory. Of course, because it's US funded, there's sometimes some other acronyms thrown in front, like the NSFDOE, Vera Rubin Observatory, like National Science Foundation, Department of Energy, Vera Rubin Observatory. We're going to call it the Vera Rubin Observatory because that is its official name, but just so you know, there are many, many other names, but an observatory by any other name is just as cool. Okay, so comment from John, you'd love to hear about VRO use in multi-messenger gravitational wave astronomy. That is one of the points that we will talk about towards the end of the stream. So it's going to be a long stream today. I'm planning like an hour and 15, an hour and 20 minutes. But y'all know I like to ramble, so this might go a bit long. And as always, even though I do have a topic planned and I have some things to talk about, you can jump in with your questions at any point. This is an interactive stream. You can ask me questions. You can jump in with comments, with anything you want to add. This is not just me monologuing. This is interactive. This is the nature of Cosmology. So even though we have a topic and I have an approximate loose thread of direction that we're going in, jump in at any point with your questions, especially if something is not clear, or just your comments. I'm going to show you some very cool videos later. Do share your thoughts, even if it's just a wow, that's amazing. Put it in the comments. I love seeing your thoughts. Otherwise, by the nature of this show, I don't get to see you. You all see me. I'm just basically talking to my screen. So I do appreciate all of the comments because it lets me know that you're still here, that you're still watching. I also have a number somewhere on the screen telling me how many people are watching, but the comments is how I really know how many people are engaged in the stream, and that helps me figure out what people like me talking about. So, point being, chat, leave comments, say hello wherever you're watching from, whatever you're doing, just leave a comment. It is always very much appreciated. And for anyone who may be concerned about me blowing my nose constantly, I am not in fact ill. It is just very hot, and it's not so hot now, but the air is very dry, and that always makes me kind of sniffy. But I am not in fact ill. If I was ill, I wouldn't be doing a stream. I wasn't be doing a stream. God, that came out in to Devonshire. There'll be my stream. Let us start talking about Vera Rubin. So I'm going to start by showing you a picture of Vera Rubin, and let's see if this works. There should be a picture of Vera Rubin on the screen now. Excellent, that works. Also, as you can see, some of the pictures today have not yet made it to my slide deck, which means they're just here. You get the URL at the top, which also means you can find the sources for everything I'm going to be showing you today, because I didn't have time to download these things. But this photo is on the webpage of the Vera Rubin Observatory. So, Vera Rubin was born in Philadelphia in the US to a Jewish family with roots in Eastern Europe. She was born on July 23rd of 1928. And she died on 25th of December 2016 at the age of 88. Now, you can see her here in this image playing about with one of the massive telescopes that she got to work on for some of her observations. This was the 2.5 meter telescope that she was working on. And anytime you see pieces of Vera Rubin and so on, there is often one image that people use, or there are two popular images. One is the one on her Wikipedia page where she's staring into a small kind of microscope type thing. And there's one where she's posing surrounded by planets, and both of those are very, very cool. But I love this image because she just looks like she's having a great time looking through this telescope, and you know, that is what she was about. She was very passionate about science. She was very dedicated, and she just genuinely enjoyed staring at the cosmos. There was a quote she gave in many interviews where she basically said, "How could you possibly live on this earth and not want to study the universe?" And I feel like this figure captures that. This image captures that. Okay, so one of the prevailing themes that we're going to be talking about today, and which we have to talk about anytime we talk about Vera Rubin, is the sexism she faced in science. Now, Vera Rubin was a pioneering astronomer. She did a lot of groundbreaking work. Her work in many regards was ahead of its time. She was often working on topics that were not yet mainstream, which meant she was already meeting some pushback for challenging the scientific status quo. She was also one of the first female astronomers in a lot of the universities where she was working, which means she met a lot of pushback also for being a woman in science, because she was basically challenging the status quo both of academia, of science, and of the male-dominated environment in which she was. There's also a discussion, which we will be having throughout this stream, about whether Vera Rubin should have received a Nobel Prize in physics. Now, the general consensus among most people in the field is that she should have, in fact, received a Nobel Prize, but she did not. And when asked why not, there's not really a convincing answer. Now, the unofficial answer, of course, is because she was a woman in science and because she constantly challenged the status quo. Of course, there's probably other reasons, but she is often considered to be one of the people who was snubbed for a Nobel Prize in the 20th century. So, or even on the early 21st, because she could have won it up until her death in 2016. Okay, so some things about Vera Rubin's history and what she was doing. First, we start off with where she first went to study her bachelor's, her undergrad, her first degree in physics, and she wanted to enroll in Princeton. However, the Princeton University had a policy that women were not allowed in the astronomy department. This policy was in place in Princeton until 1975, which is not that long ago. That's what, 55 years ago? That is less, 50 years ago? That is not that long ago. But yes, Princeton would not allow women to join the astronomy department until 1975. So when Rubin attempted to enroll in the astronomy program at Princeton, she was rejected on the grounds of, "You're a woman, we do not accept you here." So instead, she applied elsewhere. She did get offered a position at Harvard. She turned it down to work in Cornell because that's where her spouse was working at the time. So Zoomies time. I'm not sure if you can hear it, but Zoomies just started. I have my cats zooming around. Okay, so Vera Rubin joined Cornell, where she got her master's degree in 1951. After getting her master's degree, she moved to Georgetown University, where she worked on her PhD with George Gamow, and she got her PhD in 1954. So that's just a bit of the kind of trajectory, her academic trajectory. She published over 150 papers during her academic time. Zoomies going on at the side. And as I mentioned before, she did a lot of pioneering research, especially in the field of galactic dynamics and galaxies and how galaxies move about. So I want to talk about two instances. Before I get into her actual work, I want to talk a bit more about her as a person and kind of what motivated her partly to be a lifelong advocate for women in science. She's someone who advocated really strongly for women in science. And she was also a role model to many people, myself included. She is someone who motivated many women, many young astronomers to actually pursue this field and kind of prove to a lot of people that you can do cool work while being a woman in science. So there's two instances I want to talk about. I just see here there's there are very disruptive zoomies happening just right off camera here at the side. The tunnel that is supposed to be over there is now here next to me, and Otto is trying to climb into the bathroom by climbing up the door, which, it's a wooden door, you cannot climb that. Anyway, comment from Paul here that Vera Rubin can be the first winner of the newly minted Cup of Cosmology prize. Indeed. I feel like that would be a fun thing to do, like just my yearly astronomy, my yearly favorite astronomer. But I don't like rankings. I don't like these scientific prizes. So, yes, Vera Rubin did get a lot of accolades and a lot of other prizes during her life. But importantly, she missed out on the Nobel Prize, which is not overly surprising given that there's only been like 4 women in physics who have ever won the Nobel Prize, and one of them won it twice, which is Marie Curie. Question from John: do zooming cats orbit the room faster than expected? They do. They definitely zip around faster than expected. I currently have lost track of the zooming cat. Oh, he's up to mischief. He'll settle down. They've had dinner. They'll settle down. They're just kind of zooming around right now. Okay, so 2 anecdotes I want to talk about Vera herself before I get into the research that she did. Now, one of them is in December 1950. So she was still an undergrad at the time. And she had some results about how galaxies move that she thought were significant. Now, the conclusion she had drawn from these results was still incomplete and would later be disproven, but these results served as a foundation for research on the supergalactic plane. So we know we have the plane of the Milky Way, so we have this kind of galactic plane. Then there's also the supergalactic plane, which is about the motion of a lot of local galaxies in the local group. So there was this annual meeting of the American Astronomy Society where she wanted to present her results. Now, the problem is this astronomy meeting was scheduled 3 weeks after she gave birth to her first of 4 children. One of her male colleagues offered to present her results in her stead, and she was like, no thanks, I got this, I'll do my results. So she presented her results as an undergrad student, as one of the only women in the room, in front of the whole American Astronomical Society, and it was not well received. It was not well received. She was criticized for the lack of robustness. She was criticized for the results she had drawn. She was criticized for kind of going against the existing scientific paradigm, to the point that there was a paper in the actually in the Washington Post. A few days later, there was an article in the Washington Post with the title, so bear in mind we're talking here about an undergraduate lady who had just given birth 3 weeks prior, presenting her results at an astronomical conference, and the article in the Washington Post was titled, "Young Mother Has Own Theory of the Universe," in a very kind of, who's this? Who's she to tell us about the universe? Vera Rubin herself has said that this is probably, that her conference presentation was met in general with a lot of negativity. Now, obviously, you can point out here, it's valid to point out that the results she was presenting were not as robust as perhaps they could have been given more research, but she was an undergraduate student at the time. She was working towards her master's, and this was a big result and a big conference at which to present it. And she was met with a lot of pushback. And this is something that she worked a lot to try to get more women in these bigger associations, in the the American Astronomical Society and the National Astronomical Society. She pushed a lot to get more women involved in these, and part of the reason was because of her treatment in this. And then there's another anecdote on a similar note, talking again about discrimination that she faced as a woman in physics, which I think highlights her kind of funny side of her personality. Yeah, I just want to add a comment here. Like, I never had the chance to meet Vera Rubin. The anecdotes I'm telling are kind of well known among people who worked with her. Everyone who worked with her described her as being a very good person, a very warm, a very funny person. So this is kind of the where I'm getting my information from. I never had the chance of meeting her. So in 1965, Vera Rubin requested time on the Palomar telescope in the Palomar Observatory to conduct her research on galaxies. And initially, they were reluctant to let her observe using this telescope. Eventually, she got time on this telescope. She got to observe. She got to use the telescope. And when she turned up there, she was told that she wouldn't be able to stay long because the building did not have any bathrooms for women, and therefore she would not be allowed to stay in the observatory for long. She would have to leave, as soon as nature required it. Her response to this was to cut out a little paper skirt triangle thing and attach it to the icon of a man on one of the bathrooms to make it look like he was wearing a skirt. And then she said, "There's your woman's bathroom. I'm going to use that. Now let me get to work." And then she conducted observations the whole night. And I think this is a very, very funny anecdote. I just love the way she handled that. Of course, this is kind of an anecdote, so we don't know how truthful it is, but I love the way that she apparently handled this. And I just wanted to mention these two anecdotes as a reminder that this was the environment she was in. This was the type of discrimination she was facing. While trying to do her pioneering research, she was facing this kind of pushback just because she was a woman doing physics, at a time when it was still very difficult for women to be accepted in the physical community, in the physics community. But okay, let's talk about her actual research. So Vera Rubin worked on a lot of different things related to how galaxies move. A lot of what she would do was observing galaxies or distant objects in the universe and see how they move about, looking at how they move relative to each other or how they move relative to our galaxy, to the Earth. So one of the biggest things that she discovered, among other pioneering research, one of the biggest things she discovered was the discrepancy between the predicted and the observed motion of stars inside galaxies. So when we look at how stars move around the center of a galaxy, we expect them to behave one way, we've observed them to behave a different way. And this is known as the galaxy rotation problem, and this was one of the first main pieces of evidence for the existence of dark matter. Okay, so that is just setting the scene of who Vera Rubin is and what Vera Rubin was doing. Now, before I get on to what Vera Rubin specifically did for dark matter, I want to provide a bit of context as to what is dark matter. So we are going to start with the usual thing that you've all seen me do quite often, and this is where I'm just going to show two images that are the wrong images before I get to the image that I want to show. Bear with me 1 second. How fast is this going to change? Not this one. Come on, this. In the old studio, I could change image before putting it on screen. In the new studio, I cannot. So anyway, just there's going to be a bit of me going back and forth with images, and you just got a CMB flash up accidentally on screen. Okay, so we know that the universe has three main components. Everything we see, everything we're accustomed to, everything from me to the cats who have just settled down, to my tea mug, to my phone, to the stars you see in the night sky. All of this is normal matter. Normal matter only accounts for 5% or 4.9% of the energy budget of the observable universe. Then we have another 26.2%, just over a quarter, which is in the form of dark matter. Dark matter is this weird type of matter that interacts gravitationally, but doesn't interact electromagnetically. This means that dark matter is essentially invisible. It does not reflect light, it does not emit light. As far as light is concerned, dark matter is not there. However, dark matter will distort space-time, it will cause a gravitational effect, so it will cause light to bend around it. So we know that dark matter is there thanks to the way that everything else moves around it. And then we have an overwhelming 68.9%, which is in the form of dark energy. Now, dark energy is this weird type of energy that is driving the accelerated expansion of the universe, and that's pretty much everything we know about dark energy. I see we have the question here from John of how did she measure the rotational velocity in a galaxy? I'm going to get to that. That is an important point. I just want to put her work in broader context before I go specifically into her work itself. And a comment from Paul that you saw the CMB, and that counts. It was 26 minutes in. Yes, we always keep track of how long it takes the CMB to appear. And I just want to point out that the CMB is permanently in the background now because I have my CMB volleyball. This is the WMAP image. I talked about it last week, but it's sat in the background and it is visible, which technically means the CMB is constantly visible on my stream from the first second that I turn the camera on. Because then I don't need to flash the image every time I have my own portable CMB ball, which is just sat here. I thought about hanging it and having the ball like here, but I know my cats will try to jump on it. This is a collectible item. It is rare. There's only like 100 of them in existence. I'm not letting my cats attack that. I've just moved it, and one of the cats is like, "What is that?" No, no, you do not get to play with the CMB ball. Okay, so 3 main components of the universe: dark energy, dark matter, normal matter. This is kind of our pie chart. By now, this is a pretty well-established dynamic. We know these numbers exactly. Partly thanks to all of the observations done in Vera Rubin's time, and partly thanks to the cosmic microwave background radiation, which is this thing here, actually showing it properly this time. All this light in the universe is a snapshot of what the universe looked like 380,000 years after the Big Bang. And thanks to these amazing observations, which were done in the 21st century, we know how much dark matter, dark energy, and so on there is in the universe. But before we had these incredibly precise measurements, the nature of dark matter was largely mysterious and largely rejected by the community. Because, now we're at a stage where it's part of the standard model of cosmology. We know that. We're pretty sure that dark matter is there. It is the best explanation we have for a lot of different observations. It is part of the standard model of cosmology. There are some people in the field who don't like the dark matter paradigm and are looking for alternatives, but it is kind of the accepted paradigm by the majority of cosmologists. But that has not always been the case. And can you imagine the first person to propose? So I think there's an invisible matter out there that is a lot more present than normal matter. I'm going to call it dark matter. We can't see it, but trust me, it's there. Trust me, bro, it's there. Yeah, so we don't have to imagine because we know who this was and we know how it went down, and it did not go down well. Comment from Prathia, were dark matter and dark energy discovered at the same time? Not completely. Kind of around the same, 40 years, which I'll talk about in a sec, but not at exactly the same time. And their discoveries were separate events. Do I stash the CMB away when I'm not streaming? So actually, fun fact, I have a Lego International Space Station. It's like a 880-piece Lego set that assembles into a scaled replica of the International Space Station. It is on top of my bookcase. And I realized at some point that the solar panels of my Lego space station are the perfect width apart to stash the CMB in. So when I'm not in the stream, the CMB is actually being held in place by my International Space Station, and it is in a place that the cats don't pay attention to it. So yes, when I'm not I feel like this is just an insight into me being like, yeah, I'm a nerd. I have a Lego International Space Station. It's on my bookshelf, and it stashes my CMB, and this makes me very happy. This sparks so much joy, seeing my CMB stashed, being held in place by the International Space Station Lego. It's It's cool. Yeah, it's that's me in a nutshell. CMB beach ball, International Space Station, out of reach of my cats. This is who I am. And someone who likes tea slightly at room temperature, apparently. Okay, so let's talk about what I was just saying. How do you come up with the idea of, hey, what if there's invisible matter in the universe? What if invisible matter is a lot more present than normal matter? So let's go back to 1933, almost 100 years ago. You see, I say 1933 and we're like, yeah, that was almost 100 years ago. Incidentally, 2000 was 25 years ago. 2020 was somehow 5 years ago. What is time anyway? 1933. We have Franz Zwicky. Franz Zwicky. Zwicky is observing how galaxies move in the Comet cluster. So the Comet cluster is a local cluster of galaxies, or a nearby cluster of galaxies about. Why did I start on that when I don't know how far away it is? About some light years away, or the sun. Comet cluster. It's a cluster of galaxies. Now, at this point, we were getting to the stage, early 20th century, 1930, 1933. This was the time when we were starting to get really good telescopes. We could build really big telescopes. We were getting better at understanding how objects were moving. By this point, people had figured out that the universe was expanding. We weren't yet at the stage of knowing that it's expanding faster than it was in the past and that this expansion is accelerating in dark energy. We were just at the stage where the universe was expanding based on the current knowledge. So we knew that people knew that objects had redshift. I say we, I wasn't around then, I'm not that old. I know I look good, but I'm not that old. I'm not over 100 or almost 100 years old. As always, this stream is going to be a bit rambly, but you'll know what that's like by now. You know what to expect in these streams. So 1933, people knew that the universe was expanding, which means we knew that objects had redshift. Redshift is an indication of how far away an object is. And basically what you do is every light source in the universe will produce absorption and emission lines based on how it interacts with other things in the universe. And we know specifically at what wavelength these lines should appear. So by measuring kind of the spectrum of an object, we can figure out where the hydrogen line is. We can compare that to where it should be. And then that allows us to figure out how much this object has moved, or if it's moving away from us or towards us, and approximately at what speed. Once we factor in what we know about the relationship between the distance of an object and the redshift of an object, once we know the redshift, we know the distance via Hubble's law. So at this time, people could start using the redshift of objects to figure out whether things were moving away from us or towards us. Comment from Paul here: as a non-cat owner, the phrasing was fascinating. Not where they can't reach it, but somewhere they won't be interested in. Yeah, it's very curious. Cats have kind of selective blind spots. Like, they investigated the International Space Station Lego thing when they first got here. They didn't show interest in it, and now that the CMB ball has appeared there, it doesn't matter. They flagged that area as not interesting, so they don't pay attention to it. It's the same, like, there's one cat bed that is next to my table. Digression. There is one cat bed that is next to my table. They do not like this cat bed at all, unless I move the cat bed. If I put it anywhere else in the house, it's something like a new discovery, and they'll go investigate it until they're like, oh yeah, it's this one. We don't like this one. So yeah, cats have a weird sense of object permanence, but they've decided the International Space Station Lego replica that I have is not interesting, so the CMB ball on top is also not interesting. Cats, I don't know, cat logic. I'm trying to explain cat logic, which is honestly probably harder than explaining cosmology. Probably harder to understand. I know what my cats do most of the time. I know that if the CMB ball is on the International Space Station, they ignore it. Good enough. Anyway, yes, 1930s, astronomers, people knew that the universe was expanding. We knew that objects had redshift, and that by looking at the redshift of an object, you could kind of figure out either how far away it was or what it was doing. So by using this information, Zwicky was making observations of galaxies in the Comet cluster. He was able to see that most of these galaxies were moving at an average velocity, so they were kind of moving as a bulk because this cluster is moving away from us. However, due to increasing technology, he was able to separate some of the individual galaxies inside this cluster and measure their velocity. And while most of the galaxies in the Comet cluster were moving with approximately the average speed of the whole cluster, there were several of these galaxies that were zipping around a lot faster than they should have done, or a lot faster than we expect. So within this galactic cluster, there are some galaxies just moving with the flow, and then there's ones going pew, 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 all over the place, not making noise added for effect. Galaxies do not do a pew, pew, pew noise, and you wouldn't hear them anyway in space, because there's no sound in space. No one can hear you scream in space. You definitely can't hear galaxies moving. So once Zwicky had figured out that these galaxies were moving a lot faster than you'd expect, there came the question of how is this cluster of galaxies stable? Because if galaxies are moving so quickly, you'd expect this cluster to kind of pull itself apart. But that wasn't the case. The explanation that Zwicky found is that there must be more matter in this galaxy cluster than what we can see. There must be more matter than the visible matter. And at the time, based on his first estimates, he came to the conclusion that there must be 400 times the amount of this invisible matter as there is normal matter. And he coined the term dark matter, or in German, Dunkelmaterie, because he was writing in German. And this was the first written idea of dark matter. There had been some ideas, like a few years previously, Lord Kelvin had done similar research and had also found this kind of invisible matter, but hadn't actually published on it and didn't call it dark matter. But it was kind of like something that was known that he was also working on. But Zwicky was the first one to refer to this as dark matter, Dunkelmaterie. And at this point, he proposed that we would need 400 times the amount of dark matter than normal matter. Now, of course, this idea was immediately dismissed by the scientific community. They're like, why do you want invisible matter? This makes no sense. What do you mean there's 400 times invisible matter as there is normal matter? And there was a lot of criticism raised about the uncertainty in his measurement. For one thing, the Hubble constant, which was used to determine the relationship between the distance and the redshift of an object, or like the velocity and the redshift of an object, still had a big uncertainty at the time. The Hubble value was of the order of 500. We know today it's around 70. This is not that it's changed through time, just our measurement has changed through time. There was also some confusion or some lack of knowledge about the fact that the stars used to calibrate things have different types. So when you measure these different galaxies, you need to account for the fact that the stars have different spectra. So there was a lot of uncertainty in Zwicky's measurements. So his whole results were, in general, rejected by the entire scientific community. However, over the next 30, 40 years, these things would gradually get more and more attention, and these criteria, these criticisms that people had about Zwicky's model of dark matter was, so all of the criticisms were gradually addressed. So we got better understanding of Cepheids, we got better understanding of the Hubble value, better understanding of how to calculate the redshift of objects. So by around the 60s, this factor 400 was reduced to a factor of somewhere 5 to 10. Now today we know this is a factor of 6. There are 6 times more dark matter than there is normal matter. So by the 1960s, Zwicky's results, taken with new advances in the field, showed that there should be around a factor 10 more dark matter than normal matter. Still, this idea was not yet fully embraced by the community, because why do you want this invisible matter? Why? Why do you want this invisible matter in the universe? Around this time, people were also starting to think about the idea of dark energy, of having, because we were getting the first ideas that maybe the universe is not slowing down, but its expansion is accelerating. So around the same time, 60s, 70s, people started thinking about the concept of dark energy as well. Okay, comment from Scott here, or 2 questions from Scott here. The first one is, are there any galaxies blue shifted other than Andromeda and Triangulum? In general, no. So a galaxy is blue shifted when it's moving towards us. But of course, when we calculate the redshift of an object, we actually calculate 2 redshifts added together. One is due to the movement of the galaxy itself, where we can have galaxies moving towards us and galaxies moving away from us. But then there is the redshift that comes from the expansion of the universe. And because we know that the universe is expanding pretty quickly, most galaxies that are not immediately close to us will have a much larger contribution from the cosmological redshift than from their actual own motion. So even if there are galaxies out there that are moving towards us, they're still going to be redshifted because of the expansion of the universe. However, Andromeda, our neighborhood galaxy, and Triangulum, another galaxy that is quite close by, are close enough that the dominant contribution to the redshift is their own individual movement. So we see these galaxies as blue shifted, as moving towards us, because they are close enough that the main contribution to the redshift is their own movement and not the expansion of the universe. But even if there are other galaxies out there who are moving towards us on some individual level, the overall expansion of the universe means that all other galaxies are going to appear redshifted. Another question here from Scott, when I'm talking about the Comet cluster. Scott's asking here, I get that they observed it moving faster than expected, but what did they base their expectations on? So the idea here is the expectation is that if you have a group of galaxies moving, all of the galaxies inside this cluster will be moving approximately the same. And this is not what Zwicky found. What Zwicky found is there were some individual galaxies here that were moving a lot faster than expected. And if you're going to have galaxies shooting around inside a cluster, you'd expect them to kind of shoot out of the cluster and the cluster to be pulled apart. But it wasn't. And in order to explain why it wasn't pulled apart, Zwicky postulated or proposed that there was a type of invisible matter holding it together. So there's something adding gravitational force, pulling all of these galaxies back, allowing them to move around faster without pulling the cluster apart. So what Zwicky noticed is these galaxies are moving faster than the average galaxy in this cluster by a lot, and this should rip it apart, but the cluster has not been ripped apart, so there's something that must be holding it together, and this is what he described as dark matter. Okay, very good question here from John. Hey, good out, great to see you. Question from John here. How do you separate out all the different overlapping Doppler shifts in sources of light when you could have rotation, peculiar motion, cosmic expansion, and more influencing a source? So this is basically what I was just talking about, how when we look at galaxies, we have the Doppler shift coming from the galaxy moving away from us because of cosmic expansion. We have the rotation of the galaxies. We have the peculiar motion, which means the individual motion of the galaxies. And it is quite hard if you just focus on one galaxy, you get one redshift. So it is quite hard to say like, okay, the redshift of all of this galaxy comes from these different sources. What you get is the final result. Now, what we normally do is we do other observations. So an example of the Andromeda galaxy, we've been able to do many other observations because it's quite close by. So that allows us to figure out how this galaxy is moving in relation to galaxies around it. And then you can separate out the peculiar motion from the redshift, the cosmic expansion redshift. There's also things you can do where we take advantage of the fact that not all galaxies are moving away from us. Their own individual motion are moving away from us. They might have their own motion moving perpendicular to us and then the expansion of the universe pushing them away. So those are kind of things that you can combine with different type of observations to separate out what is the redshift or the movement caused by the expansion of the universe and what is the movement caused by the own galaxy. And often using clusters is a good way of doing this because the expansion of the universe contribution to the redshift should be the same for every galaxy inside the cluster. So then when you get galaxies inside this cluster that have different redshift, that allows you to figure out their peculiar motion or their individual motion. So if you ever see the term peculiar motion, which is the term John correctly used here, the peculiar motion is literally the motion of the galaxy by itself. So what the galaxy is doing independent of cosmic expansion. It's kind of like galaxies going this way, galaxies going this way, because everything has some type of motion in the universe, and there's the angular rotation of the galaxies as well. There's galaxies, crashing into each other. There's a lot of stuff happening. So the main things that we need to be aware of is when we're talking about cosmic expansion, to not attribute what could just be a galaxy doing its own thing to the expansion of the universe. And these are components that we need to be able to separate. And we can, thanks to having stared at the sky for many years and figured out how to kind of separate these different motions. One main technique is the direction in which things are moving, or filtering out the fact that a velocity is not just one number, it's a vector. So it means it kind of gives you an arrow in which way it's going. So we can use different techniques to get different parts of this velocity, and then we can figure out which part is coming from the overall expansion of the universe and which is coming from the motion of the galaxy. This is not easy. I don't want to downplay this. It's like, yeah, we know how to do that. In fact, figuring out the peculiar motion of galaxies and what is the cosmic expansion, redshift, and all of these different things, and the rotation of the galaxy is one of the reasons we need massive observatories like the Vera Rubin Observatory, which I'm going to get to later, or like the DAISY Observatory, or the SDSS Observatory that we've had in the past, or the Pan-STARRS Observatory that we've had in the past, because all of these allow us, the more information we have, the more angles from which we stare at different things, the more approaches we use to staring at different things, the more we're going to figure out how things are moving relative to us and how much of that motion is related to the expansion of the universe. So this is an excellent question, John, because it really ties into why doing this whole field is very, very difficult. And partly one of the reasons why Zwiecki's results of, hey, look, I found dark matter, or I found invisible matter, were initially dismissed because, or his theory was, we need dark matter to explain this galaxy cluster. And this was partly dismissed because people said he couldn't be so sure that the motion was coming, that he was measuring, was the individual galaxies and not some other factor like the expansion of space-time and so on. Hey, Sina, great to see you here in the chat as well. Nice to have you here. Feel free to ask questions. Okay, comment from Prathi, and then we're going to continue talking about dark matter and Zwiecki because we're about to get to the point where Vera Rubin enters again. This is just setting the scene for Vera Rubin's research. Okay, question from Prath. Are there galaxies whose blue shift from their velocity towards us perfectly cancels the redshift of the expansion of the universe so that both stay in the same distance from each other? I don't think so. And the reason is because the expansion of the universe is accelerating. So in order for these to be able to cancel out perfectly, you would need the galaxy traveling towards us, accelerating by the exact amount that would cancel out the accelerating expansion of the universe. And this would be a very, very, very fine-tuned measurement in order to have the exact amount of acceleration to counterbalance the exact amount of cosmic expansion. It's quite unlikely. Now, it could happen, but it's quite unlikely. Question from Guadav. How do astronomers organize a party? They plan it. Yeah, plan it. It's funny. I'm sorry I spoiled your punchline there, Guadav. I know that joke. Sorry. Still a funny joke. Okay, at this point, I just need to finish my tea because I made this tea almost an hour ago. It is cold. Rooibos and blueberry, for anyone keeping track. I know some of you keep track of random things like that. Okay, question from John here. Do satellite galaxies lying the Magellanic Cloud follow the same distance rotation speed relationship as outer stars in the parent galaxy? Excellent question. Very good question. And very good seg into the exact thing that I wanted to talk about. So thank you for that. Also, I want to say all of your questions are very good. All of these questions about the movement of galaxies is exactly the type of thing that Vera Rubin was asking herself. It's the type of thing that Zwiecki was working on. This whole idea of how do we separate the motion of galaxies? What's the speed of galaxies? What are they doing? How are they moving? These are the questions that people were trying to answer. So the fact that you're asking these questions is great. You're thinking like physicists. You're thinking like cosmologists. These are the questions that people want to answer on why we do galaxy rotations and galaxy dynamics. So, okay, we got to the 1960s, where people are still not really accepting of the idea of dark matter, but the idea has now been around for 30 years. Zwiecki has refined the measurements based on updated information. He's currently proposing that about 10 times the amount of normal matter should be in the form of dark matter, but it is still not widely accepted by the community. Now we enter the 1970s. Now at this point, Vera Rubin is observing galaxies, the motion of galaxies, but together with, I've just forgotten the name. Is it Kent or is it Ford? Or is it Ford Kent? There's a name that I should be aware of that has just completely escaped my brain. And it's either Kent or it's Ford, or it's Kent Ford or it's Ford Kent. But my brain has just taken that name and thrown it away. What is the name I'm trying to get to here? What is this name? It is Kent Ford. Okay, yes, William Kent Ford. This was like Ford Kent, Kent Ford, one of those. Yes, Kent Ford. Okay. Just had to Google that name because I wrote everything down except apparently the name of Rubin's collaborator. I'm doing the inverse thing, I'm ignoring him because he's a man. I don't want to talk about him today. Anyway, in the 70s, Vera Rubin is working with Kent Ford. I've immediately forgotten the ordering again. Anyway, Kent Ford. William Kent Ford. They are working together, and they have a new telescope that has incredible precision and can figure out the redshift or the movement of individual components of galaxies. So instead of all of the galaxy, they can filter out the center of the galaxy to the middle of the galaxy to the edge of the galaxy. That you can pick out individual stars or kind of star clusters at different parts in the galaxy, and they can get the spectrum of these different components, which means they can start measuring the velocity of different parts of this galaxy. So instead of measuring how the whole galaxy is moving, what if we look at the velocity of stars in the center and stars in the middle and stars in the outskirts of the galaxy? Now, first of all, Vera Rubin did these measurements on Andromeda, our nearest neighbor, M33, and then extended it to 10 other spiral galaxies. And she consistently found the same thing. The thing that Vera Rubin consistently found in every galaxy that she looks at is that stars at the center of the galaxy were moving at about the same speed as stars on the outskirts of the galaxy. And this is not what we expect. Now, what we expect is that the closer you are to the center of the galaxy, the faster you are going to move. And as you get further and further away, you're going to move slower. And this is something that is just based on angular physics, angular mechanics. If you've ever seen the thing of a ballerina is going to spin faster with the arms up than with the arms out, you're an ice skater, you put your arms out, you're going to slow down. You put your arms up, you're going to spin faster. If you're on a merry-go-round, if you go closer to the center, you're going to feel like you're spinning faster than if you go on the outside. This is angular momentum. We expect that the closer you are to the center of mass, the faster you are going to spin. You put your arms up, you've made your center of mass smaller, you spin faster. You put your arms out, you're expanding away, you're going to kind of slow down. This is something that we are accustomed to. So what we expect inside a galaxy is that the further away you are from the center of the galaxy, the slower you should be moving. Now, Vera Rubin, together with William Kent Ford, were one of the first people to be able to actually do this. Ford had developed this new telescope that allowed them to pull out individual stars inside the galaxy and measure how they were behaving, first with Andromeda and then to other galaxies. So I just want to show you exactly what this should look like. Haha, managed that slide transition very nicely there. So what you can see here is a plot that has the velocity on the vertical axis and the distance to the center of the galaxy on the horizontal axis. Now, what we expect to see, just based on visible matter, is what is shown in the dashed line you can see down at the bottom. And what we expect is that there's this initial velocity that then decreases as you get further and further out. So you can see this dashed line goes down, 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 down as you get further away from the center of the galaxy. This is what we expected to see. What Vera Rubin showed in Andromeda, which is the galaxy that you can see here, and in many other galaxies, 10 other galaxies that she looked at, was just looking at the light from starlight, which is shown here in yellow. This was not slowing down. The stars, no matter how far she was going out from the center of the galaxy, the stars were not slowing down. And this kind of led to the idea that there was something causing these stars to not slow down. Mainly, following up on what Zwicky had already proposed, was the idea that there could be some other type of matter that we're not seeing that is changing the center of mass, so that the center of mass of the galaxy is not just here, but it's here. It's this false thing. So these stars are not on the outskirts of the galaxy because there is a whole halo of invisible matter around the galaxy. The conclusion Vera Rubin drew from this was that at least 50% of the mass of galaxies is not visible starlight. It is not in the visible mass that we can see. It is not in the stars. There is at least 50% that we cannot see that is stretching out far beyond the center of the galaxy. At this point, Vera Rubin went back to the idea that Zwicky had proposed and said, this could be Zwicky's dark matter. Vera Rubin did this first on Andromeda and then on 10 other galaxies. And in every single galaxy, she was consistently finding the same rotation curve, the same idea that The stars, no matter how far away you got from the center of the galaxy, the stars were, in fact, not slowing down. Okay, coming from Prathia, expecting all the stars of a galaxy to orbit at the same rate would be like expecting all the planets of the solar system to orbit the sun at the same rate, exactly. And we don't see, Jupiter and Saturn whipping around to keep up with Mercury. So this went against the expected results. And this isn't something Vera Rubin just found once, it's something she found in every single one of her observations. And she was the first to do this systematically, to look at multiple different spiral and elliptical galaxies. And in all of them, in all of the ones that she was able to observe, which was, given the technology of the time, relatively close by galaxies, but in all of the ones she was able to measure, she consistently found this evidence that there was some type of mass not contained within the visible light of the galaxy, not contained within the visible matter. She said at least 50%, her results said at least 50% of the mass must be in the form of dark matter. Okay, question from Paul here. Were Rubin's observations detailed enough to get at the issue of whether dark matter was regularly distributed or irregularly distributed in some galaxies and not others? No. It was not that detailed. She had a sample size of 10, 12 galaxies that she could see with the technology available at the time. By now, we've been able to do this in hundreds of galaxies. And we've been able to see that the way dark matter is distributed inside galaxies does not, in fact, behave the way we expect it to. It is not as uniform as it should be. This is a whole other issue that we're dealing with today, is why is dark matter apparently distributed differently in different galaxies, and what does this mean? This is known as a diversity problem in physics, but it is not the only diversity problem in physics. Okay, comment from John here. Do gravitationally bound star clusters inside a galaxy have rotation curves like galaxies? Yes, they do indeed. So going back to your question earlier of in the large Magellanic Cloud, do we see stars moving at different velocity? We see them moving at the same velocity, even though we'd expect them not to. So this is common across galaxies, dwarf galaxies. Every galaxy that we've been able to look at, or almost every galaxy we've been able to look at by now, has this rotation curve. Rotation curves today are accepted as one of the biggest pieces of evidence for something that is not behaving the way we expect, something that is probably dark matter. Now, you can also try to explain rotation curves with things like modifying how gravity behaves within galactic scales. That is also a way of explaining rotation curves. But at the time, Vera Rubin proposed, and today we generally accept that this can be explained by dark matter. So, of course, you've now got this female astronomer trying to upend the status quo about everything people believe of the cosmological model. It did not go down well. So her results were extremely controversial. And in fact, she was told that by peers and by people who were peer reviewing her papers and by more senior collaborators and colleagues, she was told that the best way to present her results was to just present the results and not draw any conclusions from them and let everybody draw their own conclusions. Just present the data. Don't talk about this weird matter. Just present the data. Vera Rubin said, no, I'm going to present my results and my interpretation of the results. I'm going to draw conclusions from my data. So she kept presenting these papers throughout the 70s, gradually finding more and more evidence that every galaxy she looked at had this same rotation curve. By the late 70s, it was a decade of battle, but by the late 70s, people began to accept that maybe dark matter is actually where we're at. Maybe dark matter is the explanation. Part of the reason that this started to get more accepted was other information coming from other clusters of galaxies, like the Coma cluster that Zwicky had initially looked at. And what you can see here, I mentioned before that in yellow we have the results from starlight. And now you can see in blue that this curve is extended by 21 centimeter hydrogen. This is basically by radio telescopes. Radio telescopes allow people to expand this by looking at fainter stars that are not necessarily directly visible, but that can also fit this profile. So as more and more data was coming out, everything was confirming what Vera Rubin had found, that these stars are not moving the way we expect, and that the best explanation we have for this is dark matter. So by the end of the 1970s, people began to accept her results and began to accept the dark matter interpretation. Around the same time, people started to find more and more evidence that the universe was undergoing accelerated expansion. So the idea of dark energy was becoming more and more prevalent as well. And kind of by the late 80s, mid to late 80s, our new standard model of cosmology was starting to take shape. Today, we fully accept dark matter as a cornerstone of modern cosmology. I start my streams always or frequently with this picture for a reason. We accept that dark matter is 26.2% of the observable universe, 5 times more prevalent than normal matter. These are now figures that we have, that we accept. But we would not have this acceptance of dark matter, these results, this kind of evidence for dark matter, without the pioneering research that was done by Vera Rubin, despite a lot of obstacles put in her path. Okay, question from Prathia. How is the galactic rotation period of 225 million years derived? Good question. I believe it's related to, because we can see the center of the galaxy and we can see the arms of the galaxy, and we can kind of see how we are moving with respect to the center and how things further out are moving. So I think it's kind of like that, but I'm not completely sure, to be honest. No idea. We know that the galactic, we think that the galaxy takes about 225 million years to do a whole loop. I think it's related to looking at how we are moving versus how the different arms are moving. But yes, not completely sure on that. The actual looking at galaxies part is not something I work on. I've worked a lot on the dark matter aspect of things, but not on the how galaxies move. So our model of cosmology today has dark matter as a cornerstone. Our understanding of dark matter was kind of dragged forward, kicking and screaming, despite a lot of protest, by Vera Rubin. And it is thanks to her that we got this first piece of evidence for dark matter. So then there is the question, should Vera Rubin have gotten a Nobel Prize for this discovery? Now, whatever your feelings may be on whether this individual piece of research should have gotten the Nobel Prize or not, the general consensus in the field is that she should have gotten the Nobel Prize. And one of the reasons is, so one of the counter arguments that is given is, well, she found evidence for it, but we don't give Nobel Prizes just for evidence. We need an actual concrete proof, kind of completed theories. This is not true. In 2011, the Nobel Prize was given to the people who measured the expansion rate of the universe using supernova and used this as evidence for dark energy. So there was a group of people in 1998 who found that supernova behave in a specific way, and the explanation for this was dark energy is driving the accelerated expansion of the universe. This was considered one of the first pieces of evidence for dark energy, and this was given a Nobel Prize. So if we're giving a Nobel Prize to the people who measured the supernova to prove the expansion of the universe can be correlated to dark energy, why not give the Nobel Prize to the people or the person who showed that the galactic rotation curves provide evidence of dark matter? It is inconsistent. There were calls throughout Vera Rubin's life for her to get the Nobel Prize, especially after in 2011 the Dark Energy Nobel Prize was announced. Everyone was very much like, okay, so dark matter is coming next, right? No. She never won the Nobel Prize. She passed away in 2016. Nobel Prizes are not awarded posthumously, and therefore Vera Rubin will never get the Nobel Prize, which many people consider to be a big snub. And there is no rationale for it. There is no valid reason given for it. It is mainly, in my personal opinion, it is mainly because she went against the status quo too much. She went against the status quo in challenging the standard model of cosmology. She challenged the academic norms. She marched into an observatory, put a piece of paper on a bathroom and said, "That's my bathroom, now deal with it." At one point, she was denied a meeting with her supervisor because it was in a part of the building that didn't accept women, and she just waited in the lobby and said, "We'll send him down to chat to me here then." She challenged the status quo. She didn't accept the fact that she wasn't supposed to be there. She didn't accept the fact that her theories were novel and new. And in my opinion, this is why she didn't get the Nobel Prize, because she went against the status quo too much, and therefore the Nobel Prize committee snubbed her. There has been a lot of talks, especially when she died in 2016. There was a lot of talks of why did Vera Rubin never get the Nobel Prize? In my mind, she should have gotten it. But all awards, as Scott is saying here, all awards are political or popularity contests, often both. I am personally not a fan of the Nobel Prize for many, many reasons, but this is one of the reasons. And the fact that it's not just Vera Rubin, there are many female physicists over the last 100 years who could very well have received a Nobel Prize and didn't. Yeah, it's a prize that awards very specific people doing very specific science in a very specific way. So one of the reasons I'm not a fan of the Nobel Prize. But regardless of whether she got a Nobel Prize or not, Vera Rubin's work was groundbreaking, and it really allowed us to get this idea of dark matter. Now, again, science is not done in a vacuum. I am not the type of person to say, like, oh, we should elevate this lone genius above the others. Science is a collaborative effect. Zwickie's work was just as important to dark matter as Vera Rubin's was. And, all of the other astronomers who worked on this, the people who then got the data from the radio telescopes to confirm the rotation curves, people who got the measurements from the cosmic microwave background radiation to confirm more evidence for dark matter, all of these people have contributed to our understanding of dark matter. So we should not elevate Vera Rubin discovered dark matter above anyone else. But when we are talking about the history of dark matter, Vera Rubin is often not mentioned. Zwicky is mentioned as the pioneer for dark matter. Vera Rubin is not. So while I don't think we should elevate one scientist above others, we should give credit where credit is due, and we should acknowledge that our understanding of dark matter was greatly shaped by Vera Rubin's research. Okay, a couple of questions. And then at an hour and 7 minutes in, we're going to go into part 2 of the stream. As advertised, this is going to be a long stream. We're here for a while. I still have some very, very, very cool things to show you. Don't worry, we're getting to the cool stuff very soon. Okay, some quick questions here. There's a comment from Perth. The more I learn about the Nobel Prize, the more I'm certain it's a sham. Agreed. No complaints from me there. Comment from Guadav. In my personal opinion, Vera Rubin Observatory is much more prestigious over Nobel Prize. Let's get to that in a minute. But yes. There was a comment here from Guadav earlier. Maybe later we can get into astronomical work typically given to women historically, i.e. cataloguing stars and photographic plate analysis. Indeed. Or, there's the whole movie about Margaret Hamilton and how she was one of the computers that NASA used before the time of computers, because give that work to women. Yes, there's a lot to be discussed here about gender roles within science and how, for a field that is supposedly about progress, scientists themselves can be very backwards sometimes and very not progressive, despite the fact that science is all about progress. Question from Paul here. Does our own rotation complicate our calculations of rotation rates elsewhere? I imagine some rotating the same as us and some the opposite direction. Now, the good thing is our galaxy is rotating quite slowly, which means, most galaxies rotate approximately the same. But when a galaxy is far, far, far away, we get to see it clearer than our own galaxy. So while our motion does kind of affect it somewhat, we can somewhat take this into account because our motion will affect the measurements we make of every part of the galaxy, not just one of them. So you can kind of cancel it out. When we're talking about the rotation curves of other galaxies, we're talking about differences of stars in the center to stars on the outside. So our own individual speed is going to affect both of these in the same way. So it's not going to affect the difference between these two. Now, when we talk about specifically like how fast is that galaxy rotating, then we do need to take into account how fast are we rotating. But when we're comparing the differences between different parts of the galaxy, then our own motion doesn't matter so much. Okay, so Vera Rubin, pioneering research, seemed like a pretty cool person, dedicated her life to very cool research and to advocating for women in science, and was a role model to many female astronomers, myself included. Honestly, her death hit me really hard. Also, it was kind of like 4 days after David Bowie died. That was a week where I was like, no, Can we stop? Can we stop with this? But anyway, Vera Rubin, pioneering research. And it is thanks to her that we have the evidence that we have for dark matter today. So it is very, very much not a surprise that there is an observatory named after Vera Rubin. So now I want to talk about the Vera Rubin Observatory. The Vera Rubin Observatory is a massive astronomical observatory built in Chile, on one of the deserts in Chile, where there's an amazing night sky. And the Vera Rubin Observatory was initially called the Large Synoptic Survey Telescope, LSST. Now, this is the name that it was proposed by in 2001. In 2001, people proposed the Large Synoptic Survey Telescope, LSST. And the idea of the Large Synoptic Survey Telescope, as the name implies, large is big, synoptic, big field of view, survey, cataloguing the night sky, telescope. The purpose of this observatory is to basically map the sky using optical, a bit of infrared, a bit of UV, but map the night sky with the biggest field of view and the most detailed precision ever. So this was the idea, and we're going to get into how this works in a minute. So initially it was called the Large Synoptic Survey Telescope, and then there was a petition to rename it the Vera Rubin Observatory. Now, personally, I have mentioned this many times before, I am not a fan of naming experiments after one individual person, because I think it kind of downplays the fact that science is a collaborative effort. However, given that Vera Rubin's contributions have been overlooked and that she was potentially snubbed for a Nobel Prize, I think it is kind of fair to name this telescope after her, especially as it is a telescope that will be searching for dark matter or will help us understand dark matter. I'm going to get more into what the telescope is doing. So there was this big petition to rename it to the Vera Rubin Observatory, and it actually got approved. So it got officially renamed to the Vera Rubin Observatory, but to kind of keep the old acronym, the LSST, alive somehow, they decided that the data that the Vera Rubin Observatory is going to produce will be called the Legacy Survey of Space and Time, so they keep the LSST acronym. So, recap, Vera Rubin Observatory, formerly known as Large Synoptic Survey Telescope, is going to produce the Legacy Survey of Space and Time, which means we can still use the LSST acronym, but in this case for the product and not for the observatory itself. So, the Vera Rubin Observatory is an optical telescope. Its main mirror is 8.4 meters. It is massive. And it is basically trying to take a survey of the entire southern sky. And it has incredible technology, which means it is the fastest telescope we have. So in the order of 2 or 3 days, it can map the entire southern sky. And it is going to do this for 10 years. So the idea behind this is that every couple of days for 10 years, we're going to get a new all-sky map, a new map of the entire southern hemisphere sky. Every few days, this is going to be updated for 10 years. By getting so many images, it means we can stack them on top of each other, which allows us to get incredible depth of view. Because if you just have one view, one image, that's good. If you can stack 10 of them, you get more pixels, you get more precision, you can stare at things. And the Vera Rubin Observatory can take many pictures very quickly. So every night is going to take thousands of pictures, and these are stacked so that we can see how the sky is behaving. And by taking these over the span of 10 years, basically the Vera Rubin Observatory is going to produce a movie of the night sky that lasts 10 years with a resolution of every few days, which is insane. We're going to get this amazing picture of the night sky updated every few days for the next 10 years. Amazing. Comment from Paul here. I hope they have a big hard drive. Glad you brought that up, because I have that number ready. I have the number of the incredible amount of data that the Vera Rubin Observatory is generating. So every 24 hours, the observatory generates 20 terabytes of data. Every 24 hours, 20 terabytes of data. It is going to run for 10 years. That is a lot of data to process. That is an insane amount of data to process. But it is the biggest wide field view telescope with incredible speed, and it can allow us to stack multiple images for added precision. So let me just answer some questions, and then I'm going to come back to more stuff about this amazing observatory. Let's see, where were we? We had a comment from John. How do ground-based telescopes like Rubin deal with the increasing number of satellites in their view, especially with Starlink? Does this affect Rubin more since it's looking at so much of the sky? Yes, it does. It's a problem. It's a problem that one billionaire decided he owns the sky and he can do whatever he wants and nobody can stop him. It is a problem that we now have these satellites like Starlink that are causing contamination. So it is absolutely something that we have to deal with. By stacking the images, we can get rid of them somewhat, because if you have a fast moving object, it will be gone by the second image. So then it's easier to remove. And the fact that Vera Rubin can stack images makes it a bit easier. But it is a problem that we will have to deal with now. Also coming from Guardafio related to this, the field of view of these large telescopes is very small, so satellite trails are rarely observed, but I believe those frames are discarded, yes. In this case, it's not a very small field of view. The whole point of this is that it has the biggest field of view, which is what allows it to very quickly capture the entire night sky again and again and again. But yes, when the 10-year movie is finished, I really want that Looney Tunes, That's All Folks closing screen to come up. Yeah, that would be funny. Now, yeah, it's amazing. Just the amount of data that this telescope is taking is really impressive to think about. So just some quick facts about this telescope. Here it is up on screen. You can see the URL of where I'm taking this from. This is from the Vera Rubin Observatory webpage, which is just rubinobservatory.com. It is a really cool webpage. They have an insane amount of information there. I highly recommend checking it out. Anyway, you can see the URL. You can see my source here. So this is an optical telescope, 8.4 meter mirror. It's going to generate 20 terabytes of data every 24 hours. It was initially proposed in 2001. Construction began in 2015. The first tests were carried out in October 2024. I'm going to pause here before getting to the big stuff. Here you can see it sat atop this little mountain, or this mountain range in the Chile deserts, and you can see they've built the whole kind of base around it and the observatory in the middle. So the question now is, what's the point? What are we doing with this? So the Vera Rubin Observatory has 4 main goals. The first one is to understand the nature of dark matter and dark energy. No small feats, just like, let's just understand dark matter and dark energy. Hey, this is goal 1 of 4. We're going to be doing a long stream today. I still have cool videos to show you. So, in order to understand the nature of dark energy and dark matter, what the Vera Rubin Observatory is going to look for is galaxies that have been distorted. Galaxies that have been distorted due to gravitational presence of something that we can't see, which is dark matter. This is called weak lensing, and it's something we have already used before, where we look at how distorted the light coming from galaxies is to figure out what dark matter did to distort it, or how much dark matter there is. So, Aguada, if you say please delete if links are not allowed, your links just don't show up in the YouTube chat. YouTube removes them automatically. If you try to put a link during a live chat, it just goes. I'm guessing you were putting the link to the Rubin Observatory. I'll throw it in the description of the video later on. But yeah, if you put a link in YouTube chat, it just gets rid of it immediately. Okay, so one of the cool things about the Vera Rubin Observatory is the amount of galaxies it's going to be able to photograph. I'm going to show you in a minute what I mean by this, and it is a huge amount of galaxies it is going to be able to photograph, which means it will give us a lot of places where we can look at how dark matter is behaving. So one of the biggest goals of the Vera Rubin Observatory, and the reason it's named after Vera Rubin, is because it's trying to understand weak lensing. It will also measure a lot of supernova, which will help us understand things about how the universe is expanding. So it will also help us understand dark energy. Excellent question here from David Howden. Why do I call it weak lensing? Is there also strong lensing? Yes, there is. Yes, there is. Short version, that weak lensing is the one that we're more likely to see on individual galaxies, whereas strong lensing is a slightly different phenomena that we usually look at in a slightly different way. Yes, we can have both. There is weak lensing, there is strong lensing. I'd have to look at a convincing way to explain this, because right now I can't give you a convincing explanation. There is a strong lensing. It is not part of this discussion, though. We leave that. We park strong gravitational lensing for another day. The Vera Rubin Observatory will use weak lensing, and it will look at supernova to try to figure out dark matter, dark energy. Okay, couple of questions here. Again, this is goal 1 of 4. Comment from John here. At the end of the mission, could you stack the 10 years worth of images to get one very, very long exposure of the entire southern sky? You could, but there's a problem with that. We don't necessarily want every image stacked into one, and you'll see why when I get to the other of the 4 research goals. So pin in that one. Coming from Paul here, I'm imagining that the breakthrough isn't how to get a wider aperture, but how to capture and deal with all that high-res data. Exactly. That is one of the big issues of how do we deal with all of this amazing amount of data in this way. If I promote a chatter to moderator, they can post links. Is that so? Okay. I do not have that option from the restream control panel. I guess that's something I would have to do inside YouTube. My options here are to basically block or put you in timeout. And I'm not doing that to any of you, but I can't promote you to moderators from this side of things, at least not currently. You were sharing an example of satellites ruining your photo of Andromeda. 7 satellite trails in a 5-minute exposure. Yeah, that's nasty. Unfortunately, it's a very common problem now if you're doing any type of astrophotography that you're going to have satellites in the way. And it's very, very unfortunate and very annoying. So, okay. Goal 1 of the Vera Rubin Observatory, understand the nature of dark matter and dark energy. If that's not enough, goal 2, it is going to create an inventory of the solar system. Basically, it is going to be our biggest tool for detecting asteroids within the solar system and other bodies in the solar system. For an example, the alleged planet 9, the 9th planet that may or may not be hiding on the outskirts of our solar system. If it's there, Vera Rubin will find it. So, it is also going to be one of our best tools for finding local asteroids. Target number 3, it is going to map the Milky Way. A comment from Prathia, wouldn't precession of the Earth's axis show up on the 10-year image? Yes, that is one reason why we can't stack the 10 years of images, but also because of objective 4. But first, objective 3 is going to map the Milky Way. By taking so many photos, it's going to see the arm of the Milky Way. It's going to gradually see how this changes over the 10 years. So it's going to help us map the Milky Way itself. And number 4, Vera Rubin Observatory's 4th target is to look at objects that change position or brightness over time. So stars that change. This can be anything from variable stars to supernova to gamma ray bursts, to follow-ups to gravitational wave observations. If LIGO and VRO find something, they can send out an alert to look for something as well in Vera Rubin data. Okay, so four objectives. Understand the nature of dark matter and dark energy. If that's not enough, find all the asteroids we can in the solar system. They're going to find about 100 times more asteroids than what we've already found. Map the Milky Way and study variable stars, supernova, and similar things. Because why not? So it's no small feat. It's planning to do a lot of cool things. There's a lot of stuff that the Vera Rubin Observatory is going to give us. Plus, as always with telescopes, there's all the stuff that we haven't thought of yet that it's going to give us. All of the unknowns that we might find. Comment here. It will find where the Roswell aliens are hiding. Yeah, maybe. So don't tell the conspiracy theorists. Comment from John here. Will the Vera Rubin Observatory be useful for find lots of occlusions by solar system objects to study their absorption spectra? Yes, that is also something it can do. When we say like it's going to map the Milky Way, that is one of them. There's also the really cool thing that in order to see how these stars change, what you basically need to do is look at 2 images of the night sky and see if any stars changed in them. And for this, Vera Rubin is opening it up to the public to help. So they're going to be part of the Universe Zoo. If you don't know, the Universe Zoo is a webpage where you can do citizen science. So it's basically images that need to be stared at by somebody. And instead of having a scientist stare at these images, they put them on the Universe Zoo. And anyone, you can create an account, you can do this for free. You can look at an image and basically flag things. This has been done for finding exoplanets. It's been done for finding galaxies that have weak lensing. And it's going to be done with the Vera Rubin Observatory data to find stars that change. So basically, if you want to help with this, you can. And you'll get shown five images of the same patch of sky and ask the question of spot the difference. And it's not a test, you just see if there's any difference. And if a couple of people flag it as a difference, then it goes to get reviewed by a scientist. Kind of, if enough people flag it, then it's like, hey, look at this one. And it will go up in the priority of images that scientists will be looking at. So this is known as citizen science. And when you have this insane amount of data, we need people to help with this. There's a bunch of projects already on the universe too. Check it out if you haven't done so in the past. It is super fun. During my undergrad, we all got really into this and we were like, who can process the most images of potential planets in an hour instead of doing our actual coursework. Super, super fun. Check out the universe zoo if you haven't done so beforehand. Okay, so I gave you all of these cool facts about the Vera Rubin Observatory, and I said at some point I'm going to stop here. So let's just go back to where I said I'm going to stop here. It was proposed in 2001, construction began in 2015, the first tests were done in October 2024, and then we had first light. Now, first light is when the telescope is turned on and starts taking actual data, and this data is released. We have already had the first 4 images from the Vera Rubin Observatory. They were released in June 2025. They were released 6 weeks ago. The first images of the Vera Rubin Observatory, we already have them. So, should we check them out? Of course, we're going to check them out. Now, they release these 4 images. Each image is around 25 gigabytes. If you go to the Rubin Observatory webpage, you can zoom in as much as you want on these images. I highly recommend doing it because it is amazing. But rather than doing that live, I'm going to let the Vera Rubin Observatory people do that for themselves, which means I'm going to show you the video. So here we go. Let me bring this up. These are videos on the official Rubin Observatory webpage, as you can see from the URL. I'm going to show you 2 of the 4. The first one is the Cosmic Treasure Chest. And what this is here, wait, can I put myself on the right? I feel like I'm blocking the text here. Can I put myself on the right? One sec, I just want to move where I am. There we go. Now no longer blocking the caption. Oh, that is nice. I complained about all the changes to the new studio, but that is nice. The fact that I can put myself anywhere on the screen, that is nice. Nice feature. Okay, so what we're seeing here is a stacked version of 1,100 images. And we're going to start with some galaxies and then we're going to zoom out. And I want to point out an important thing that you can see here in the caption, that the amount of galaxies you're going to see in this video is less than 1% of the amount of galaxies that Vera Rubin is going to observe. Let's. You can hear the cool music that is happening. Why is the video not playing? There we go. It's just the amount of galaxies in this image, and this is less than 1% of the galaxies that Vera Rubin is going to observe over the 10 years. There are already 10 million galaxies in this picture here. 10 million galaxies, and this was taken over the span of a couple days. 1,100 images went into this. That is, in my mind, still so very amazing. Let's go back to me here. So I played that one because you can really see them zooming in, zooming out. I hope it came across clearly with the new setup. Had to figure that out. That was 10 million galaxies that they're just casually like, oh, look, here's 10 million galaxies that we stacked in 1,100 images. We did this last week. We're going to be doing this for the next 10 years. The amount of galaxies we're going to get pictures of, the amount of information we're going to get is amazing. This is so cool. And this is not, they're not doing any science with this first image yet. They're just like, look what we're going to do. Are you impressed yet? Are you impressed yet? Well, if that one of the 10 million galaxies that they just casually found, if that one didn't impress you, let me show you the Trifid and Lagoon Nebula, my favorite of the 4 images. So each of these 4 images has its own webpage on the Rubin Observatory webpage with a detailed explanation as to what we're looking at, how the image was built, the photo that you can zoom into, that you can download in the 24 gigabyte resolution if you want to. And for each of these 4 images, they have this video. So I've just shown you the one advertised as the cosmic treasure chest. Here's 10 million galaxies that we casually photographed last week. We're going to do 1,000 times this over the next 10 years. Love it. So now let me show you my favorite one. And please do share your reactions to this video in the comments, because I want to know if you're appreciating these videos, if it's working, let me know if there's any issues. I'm personally loving these videos. Okay, so now we need to get into the Trifid and Lagoon Nebula. So what we're going to see here is a 5 gigapixel image that combines 680 exposure, so 680 images taken in about 7 hours. And they say in the page of this video, no other observatory is capable of producing an image of such a wide area so quickly and with this much depth. So let's get into it, shall we? Let's get into it. I'm going to show you the Trifid and Lagoon Nebula. You can see the size of the moon for comparison, just to show you what this looks like on the night sky. I'm just staying quiet and letting the video speak for itself. I know there's no audio on the video. Okay, so it's just like, oh, casually, here's the most impressive image you've ever seen of 2 nebulas. It took us 7 hours of observing time to make this. This is if there's sound on the video, we're not hearing it. Yeah, I know the sound on the video, I turned it off because otherwise my computer gets very upset. But the sound on the video is just some like background audio to just set the scene. There was no commentary, there was no description of the video. It was just some kind of soothing music. But my poor old laptop is already getting a bit upset with sharing 3 screens with all the images, so I turned off the sound intentionally. And I wasn't talking because I was just like, enjoy this video. That is so cool. I am not over how cool that image is. And this is 700 images that they took over the span of 7 hours. It's amazing. It's amazing the amount of detail there is, the amount of information that they have here. And when they zoom out on the galaxies, it's like, let's just start on a galaxy now. Let's zoom out. Here's 10 million galaxies. This took us a week. We're going to do this for the next 10 years. The second one I showed you of the nebula, let me just put the still image up. Let me just put this image up again. If it wants to share it here, come on, bring it back. The amount of detail here, and you saw in the video they zoom in and they don't lose resolution, and then they zoom in on another patch. This is just 7 hours of data. They're going to do this for 10 years. It is amazing. I love this. I love the amount of data we already have. And these are just a proof of principle. Can you imagine how much information we will have by the next 10 years when this is done? I'm excited. I hope you're all excited as well. I hope you appreciate that this image is really cool. It's amazing. I love it. Some comments here. Question from John. Will there be any way to get spectral or do photometric filtering with VRO data? The Vera Rubin Observatory data is made fully public with a 2-year embargo. So the scientists themselves have 2 years to process the data themselves, and then it will be made public. All of the Vera Rubin Observatory data will be made completely public with a delay of 2 years. Comment from Wadaf here. You love photographing galaxy clusters because when you show it to people, they inevitably start talking about how insignificant it makes them feel. Yeah, how insignificant, but to me also how connected we all are to the universe. It's amazing. It's so cool. Question from John here. Is the Trifid image in the video one telescope field of view or a mosaic of several fields of view? Given that they took 7 hours and that the telescope, I think it's a couple of fields of view stacked together. Yes, because it took them 7 hours, so it's shifting slightly. What happens to the VRO when the 10 years of data collection are done? I have no idea, actually. I didn't think to ask. I have no idea. Will probably gradually be decommissioned, and then probably the parts might be reused or scrapped or put in a museum somewhere. I'm not sure what they'll do with it, actually. But it's amazing. I think that it's a shame that Vera Rubin is not around to see this, but I'm glad that her legacy is going to live on with this telescope, with this amazing observatory. I love it. I love the Vera Rubin Observatory. Just look at this image. If you want to download it and set it as your phone background or your screensaver, you can download it from the Vera Rubin Observatory, rubinobservatory.com. You can find the videos, you can find all of this, and it's amazing. So to recap, let's bring it all together. Vera Rubin was an amazing astronomer who had to fight against a lot of sexism in order to do her groundbreaking pioneering work that gave us one of the biggest pieces of evidence we have for dark matter, which is now part of the standard model of cosmology. Despite the fact that she was potentially snubbed for a Nobel Prize, her legacy has been preserved by naming the Vera Rubin Observatory in her honor. It is an observatory that is going to take the most detailed map or picture of the night sky over the next 10 years so that we can create a movie of 10 years of night sky. We got the first release already a few weeks ago, and the images are so good. They're tantalizingly amazing. They're a promise of what's to come, and what's to come is looking so good. It's going to be a really, really good decade for cosmology and for astronomy, and we're going to have these images. And I, for one, cannot wait to see what we're going to do with all of this. As you can all tell, I'm kind of excited, I'm kind of hyped. I don't work on the Vera Rubin Observatory. I'm not going to be dealing with the data, but I'm going to be enjoying every image and video like this that comes out because it is amazing. And I hope I convince you that this is amazing. And it is very, very cool. And I'm so happy that we did the stream today because I had looked at the images, but I hadn't had time to kind of process, like absorb these images and their impact. And last week, someone asked me, I can't remember who, someone asked me about the new first results from the Vera Rubin Observatory. And it's like, yes, let's do a whole stream about this. We have to do a whole stream about this, especially because it would have been Vera Rubin's birthday recently, 23rd of July. We had to do it. We had to do it today. It's going to be amazing. Prathia saying they should upgrade the telescope and go for 10 more years. As Guadav is saying, 10 years is probably minimum. They will potentially go for longer if the parts are still usable. But at some point, every technology degrades and is replaced. So it's planned for 10 years. Maybe it will go for a bit longer if it can. But even if it just goes for 10 years, it's going to be amazing. And I completely understand the quote from Vera Rubin of, how could you possibly live on this earth and not want to study the universe? Like, how can we not wait to see the new pictures? It's times like this, it's images like this, it's stories like Vera Rubin's of perseverance, of determination, of passion for science. These are the things that remind me why I love my job and why I love being a cosmologist and why I love getting to share this with all of you. And on that note, do you all know it has been 10 years almost since my first live stream, since the first time I turned on the camera and started very nervously to say, hey, I'm a cosmologist, ask me anything you want. The exact date will be the 14th of August. We will reach the 10-year anniversary of Cup of Cosmology. And some of you have been here since the start. Some of you have joined recently, however long you've been here. Thank you. I appreciate you being here. Next Sunday, we're going to do an anniversary special. We're going to celebrate 10 years of Cup of Cosmology, which means I'm going to show you some slightly embarrassing clips from the early days because the early streams are not online. You only have the last 3-4 years of streams online. But I have them all on a hard drive. So we're going to do a trip down memory lane next week. If you have any anecdotes of Cup of Cosmology, anything you want to share, any memories of like, oh, I first joined this time, feel free to tell me. Let me know. Send them to me in advance if you want. contact@cupofcosmology.com, and I will mention them, or I'll try to incorporate them. If you have anything you want to share on the 10th anniversary of Cup of Cosmology, let me know. We'll be celebrating 10 years of Cup of Cosmology next Sunday. Okay. Thank you everyone for joining. This has been super, super, super fun. It's been really nice to have you all here, to have all of these questions and all of these interactions. I hope I convince you that Vera Rubin, oh wait, whoops, that did not go to plan. That did not go to plan. I tried to do something clever. It backfired. I'm not going to try that again. Tried to do something clever, did not work. Never mind, we'll work again. Okay, so it's been super, super nice to have you here. Loved all of the questions, loved all of the comments, loved all of the directions that we were going with the conversations here. And I hope I've convinced you that Vera Rubin was great and the Vera Rubin Observatory is going to be great and that it is a great time to be a scientist. So thank you everyone for joining. I hope, thank you for the congratulations, David Howden. Sorry, you'll miss it next week. I hope to see you all again next Sunday, same time as always, for the 10-year special of Cup of Cosmology. And I hope in the meantime, you all take care of each other and stay curious. And instead of ending on the Cup of Cosmology logo today, we're going to send it off with this image because it is an amazing image. Thank you everyone for joining. It's been great to see you all. Hope to see you again next week and stay curious.